This topic's all about the transition metals. I think it's quite an interesting topic to finish on. The transition metals are one of the major groups in the periodic table. They contain the most elements out of any other block in the periodic table, and you've probably been aware of them since about year 9. You've probably been able to spot them on the periodic table. But beyond that, you've never really looked in any great detail about their chemistry or how they behave. So after 7 years of wondering, you're finally going to learn the secrets of the transition metals. I mean, there are a few things you probably do know already. You probably know that they all contain d electrons. You probably know that they're found often in catalysts. You hopefully know that they can exist in a range of oxidation states. And you hopefully also know that they often form colourful compounds. Though as we go through this topic, you're going to add some new bits of information to your knowledge about how the transition metals behave as chemicals. What we start with is kind of a little introduction to the transition metals, and lots of this you will know from your prior knowledge. First thing we start with is a wee definition of what actually we mean by a transition metal. It's maybe a little bit different to what you're expecting. It's not as simple as something which is found in the D block, in other words has d electrons. This is definition here. It's an element that forms at least one stable ion with a partially filled D subshell. So it's an interesting definition. They have to have some bit of their D subshell being empty or only partially filled. A little bit of revision of your electronic configurations. So again, just remembering your correct order of filling that. That's not something you've not done that much this year. Remember your order: 1s, 2s, 2p, 3s, 3p. Now you always write 3d then 4s, but you have to remember that the 4s, interestingly, has a lower energy level than the 3d subshell. So your 4s will be fully occupied first. That's why this one's 4s2, and then you go into the 3d subshell. So we'll go through these ones and show you their electronic configurations. If you find that a bit boring, you can obviously skip forward and look at the end result. Scandium, you've got your 4s filled up first, then you've got your 3d one. Titanium, we're going to add another one to 3d to make it 3d2. Remember, they occupy singly before they pair up. Vanadium, we're going to put another one in. Now chromium is our first interesting one. According to this pattern, we should put 2 in the 4s and then 4 into the 3d. You hopefully remember we bit from AS1. Chromium quite likes to obtain that stable half-filled configuration. So what it does do instead, it promotes one of the electrons from 4s to go into the 3d subshell, which is a higher energy. The effect of that is that you end up with both subshells being half occupied. And that is quite stable compared to having one empty orbital left over at the end. So chromium is an exception. Manganese goes back to being normal. It puts that electron back into that 4s and then has that half-filled subshell for the Ds. Iron, back to normal. We start having to pair up our 3d electrons. Cobalt follows the same pattern. Nickel, same again. And then copper gets interesting as well. It does the same kind of trick that chromium pulls. If I put an extra electron, according to this pattern, I should have 9 electrons in this 3d subshell. However, what copper does, as well as putting that 9th one in, it's going to promote one from the 4s orbital to give it a full subshell in the 3d level. So it removes one from 4s. That allows it to give an extra electron to put 2 extra electrons compared to nickel into the 3d subshell, giving it a fully occupied subshell, which is quite stable. Zinc just completes the set by filling up both your 4s and your 3d subshells. We've got a little line here. Recall why in terms of energy levels are the 4s orbitals filled before the 3d orbitals. It's nothing too mysterious. It's literally just a consequence of the 4s subshell having a lower energy than the 3d. One thing to remember though, when you're emptying these subshells, in other words taking electrons out to form positive ions, slightly confusingly, whilst you're putting electrons into the 4s first before the 3d, you also take electrons out of the 4s first before the 3d. They're always filled first and emptied first. So I'll write them first. However, 4s is also emptied before 3D. The reason that is quite confusing, once electron subshells are occupied electrons, their energy levels actually change a wee bit. So after you've got electrons in them, the 4s subshell actually gains a much higher energy in 3D. So it's going to come out first, but you don't need to worry about that. Now, because of that rule about taking out electrons, there's a couple of interesting consequences just to focus on. If I take scandium, now, scandium, you won't know this, but just so happens, it generally forms one stable ion. Scandium 3+ is the main ion of scandium. If you think about the electronic configuration of scandium 3+, you're going to remove these 3 outer electrons. That will give it an empty 3D and an empty 4s. If you look back to our definition of a transition metal, an element which forms at least one stable ion with a partially filled D subshell. If we compare that definition to what we got with the scandium 3+ ion, the scandium 3+ ion has no D electrons. They've all been removed, well, only one in the first place. Therefore, technically speaking, because this is the only main stable ion of scandium, scandium is actually not a transition metal. Similarly with zinc, something you don't know off the top of your head but is true, the main zinc ion that's stable is zinc 2+. If I'm getting zinc 2+, I have to remove 2 electrons. The 2 electrons I remove according to my rules has to be the 4s electrons. That will leave you with 3d10 as a configuration. Again, comparing to our definition, a transition metal is something with an ion with a partially filled D subshell. The zinc ion, which is the only ion of zinc, has a fully occupied D subshell. So it's a full subshell. So therefore, zinc is also not a transition metal. Which may be a little bit of a plot twist you weren't expecting. What we're now saying is that even though we're calling this the transition metal block, these aren't all transition metals. Scandium's not transition metal, zinc isn't either, and some of the other ones down the group will not be as well. Technically speaking, we should call this the D block and not the transition metal block. It just so happens that almost all of them are transition metals, not scandium, not zinc though. So if we look on the second page, we see a little bit more explanation of that. Again, just emphasize that fact again, when transition metal ions form ions, it's the 4s electrons that are lost before the 3d electrons. So if you do a wee bit of practice of forming your electronic configurations, we've already looked at the scandium ones. You remove both the 3d and the 4s electrons. I'm not going to draw out all the configuration, I'm just going to use my shorthand you might remember from last year. If we look at the closest noble gas to transition metals, before we get calcium, potassium, the previous noble gas is argon, so I can use that wee shorthand of the argon configuration and just add on my electrons to it. So scandium 3+ has removed both the 4s and the 3d, therefore it does have that argon configuration. Fe2+, it's 4s2 3d6, taking away 2 electrons, we'll just leave it with 3d6. Cobalt 3+, I'm going to take away 2 4s electrons and a 3d electron, which again leaves it with 3d6. Then copper plus is 4s1 3d10. If I take away 1 electron, it's going to take away the 4s1, leaving it with 3d10. And again, you might spot there that's a D subshell, which is not partially filled. So we wouldn't consider scandium 3+ and copper plus to be transitional because they've not got partially filled subshells. I do think it's maybe a wee bit misleading though. I'm just going to clarify this. Whilst copper plus isn't what we call a transition metal ion, copper as an element is still a transition metal because it does have a stable ion, which is copper 2+, which is 3d9, which is partially filled. So whilst copper plus isn't necessarily a transition metal ion, copper element still is because it's got this 2+ ion. So the final thing to look at just about their introduction is just their key kind of characteristics or properties, which we've covered some of them already. The first bit is they have partially filled D subshells in their atoms/ions. We've looked at that in a bit of detail. Something you know from last year when we looked at redox, they have variable oxidation states. For example, one you're very familiar with from this year as well, chromium, which is often used to oxidize organic reagents, has oxidation states of +3 and +6, and there's different colours as you go between them. Manganese is another one you've used in lots of redox titrations. It's got a few stable oxidation states, +2, +4, +7. And then another one you've been familiar with since GCSE is that iron itself exists in the +2 or +3 oxidation states. So a lot of variability with their oxidation state stability. We've also got the fact that they have catalytic activity. Again, that's something we've covered in bits of detail before. Common catalysts that are transition metals would be iron in the Haber process, where you're making ammonia from nitrogen and hydrogen. Another one you might be aware of is nickel, used in the hydrogenation of alkenes. A little bit of terminology just to revise over just about catalysts. Just to remind you, you've got two types of catalyst to study in chemistry. You've got homogeneous catalysts and heterogeneous catalysts. Homogeneous catalysts are in the same state as the reactants. And heterogeneous are the opposite, they're in a different state to the reactants. The vast majority of catalysts you'll come across in chemistry are heterogeneous. For example, these two are iron is solid here, you're reacting with gases. Here again, nickel, generally alkenes are gases, nickel is a solid. You can get some homogeneous catalysts in transition metals. You can get metal ions dissolved in solution, which can act on ions in solution. So that would be the same state. Most of them will be heterogeneous though. Final wee point there, they often form colour complexes. You're very familiar with this, copper sulfate being one, it's blue in the hydrated form. Lots of examples similar to that.